Welcome back. Now the final leg for this morning sessions, and after this we all go for lunch. And now I welcome Dennis Ljungmark for presenting. Give a big hands, please.
Thank you. Let's see. Of course it went to sleep. Ah, there we go. Can we get this in the middle? Is that possible? No, that's wrong. This one over there, and then we start presentation, and we do with the slide notes. Okay, clearly not. Computers. Why would they work? I'm just going to stand on stage. It worked all the way until now. Okay, the full slide is at least in the picture, so let's go. I am Dennis Spindel Ljungmark. I work at Modio, one of the founders of a small startup. We do embedded and security consulting. We build embedded devices and put them online and try to make sure that others don't manage to leak your data out, which involves doing a lot of security stuff in Python and others. So, can I have the next slide, please? Yes. So, what is TLS? TLS is an IETF standard. It's made to make cryptography useful. It's not just one standard, it's a collection: ciphers, hashes, mandatory message authentication codes, access elliptic curves. We have algorithms of various kinds. We have handshaking, we have certificate handling, we have negotiations, extensions, exchange formats, multiple of most of these. There are anonymous modes and various interesting things that nobody ever uses. So, some history. SSL version 2 is the first SSL that was ever released. It's released same year as Python 1. Well, the year after Python 1.0. This puts it somewhere in the date. So if you ever see SSL version 2, imagine running your code in a Python 1 interpreter. Just sit down, look at the code, try to get it running, and then give up. It's released by Netscape for Navigator 2.0. It's the year after Commodore went up. The US still had export restrictions on cryptography and under the Arms Control Act, because Iran was a big bad meanie and there was a war going on in Bosnia. So you had to make sure that nobody ever could encrypt data because, well, we don't want our investigation people to figure it out. It has been deprecated for 20 years now. So, to state this, SSL v2 has been deprecated for 20 years. SSL version 3 was also not a standard. It has been published afterwards as a historical document because, yay, 96. The year before Python 1.5. We're still in the ancient version. It's also deprecated for 17 years. We're talking that flip phones just appeared the same year as SSL version 3. And that also contains mostly broken cryptography because, well, artificial limitations on how good the crypto could be, as well as pretty broken handshaking. And well, this is mostly because the first crypto wars. Cryptography was munitions. So export restrictions happened until the Wassenaar Agreement, and that happens both from Europe and US. Pretty much everything sold and built in that time era was broken. We're talking about clipper chips in phones to do forced key escrow, so the state would have copies of all your private keys in case they wanted to look at what you were doing afterwards, or wanted to decrypt your encrypted communications. If you're noting any current trends about cryptography and key escrow, yes, it's all happening again. So, TLS 1.0. This is the first standard TLS. This is the one standardized version. Mostly the same as SSL version 3. Some of the blatant problems fixed. And most importantly, no export restrictions. The Wassenaar agreement has happened, and we have things. So, this predates Python 2.0. But you'll see some familiar faces: DES, triple DES, MD2, MD5, RC2, RC4, IDEA. Well, wait, all of those are broken. None of them are current. All the cryptography standards that are used in TLS 1.0 are outdated and broken. TLS 1.1 goes ahead, 2006. This dates it before Python 2.4. This is before dictionary comprehensions and many of the other nice comprehensions. It fixes quite a few security issues in TLS 1.0. It does not deprecate any of the ciphers or functionality, but it fixes some of the broken modes and handshaking. So this brings us to TLS 1.2. Current release, introducing new ciphers, modes, improving security all over, deprecates quite a few insecure features. It introduces extensions. Quite a lot of extensions have been added since, mostly notably right now to do the HTTP2 upgrade feature. It was once more patched in 2011 to fix a couple of more security issues, but this is it. This is current. So, since then, we've seen quite a few cracks in the shell. TLS has its own RFC about attacks on TLS. We're talking about a standard that has a standard that combines attacks on the interfaces and cryptography in order to help work around it. So the standard has standards about why it's broken. We've seen Beast, Crime, Breach, Poodle, SSL version 3 downgrade attacks, RC4 broken, Logjam, Freak, Ghost, Drown, MD5 broken, SHA-1 broken. We've seen a couple of implementation issues. All the ones on there are not implementation specific, they are only on the protocols and the cryptography itself. Heartbleed, go to fail, various CI trust issues have all happened in implementations where they have messed up. But these are various attacks right now. You'll see them. So, since then we've cleaned up a bit. Because a couple of downgrade attacks that made it possible to force clients to accept broken crypto or even no crypto at all. We, in all implementations, have basically dragged out SSL version 2 and 3 behind the shed and shot them in the neck. Quite a few software pieces found this discomfortable because they used the functionality. Well, they hard linked to the functions that called SSL version 2 things, which were simply removed from most APIs because that software is broken, it should be broken, which caused headaches for various Linux distributions and software vendors who were shipping SSL version 2 enabled when OpenSSL and others simply removed the functionality. So we still have TLS version 1.0 because Windows XP. Oh, not only that, Android too. TLS version 1.0 requires specific. It's before you could actually provide a domain name that you wanted to talk to. So every site that needs TLS support requires a unique IP address, which is painful in modern society. We're sort of running out of IPv4 addresses, and well, IPv6 support isn't there in TLS 1.0 because most of the implementations are older. Windows XP's IPv6 implementation is nothing to drag home with. TLS 1.1, also known to be slightly broken. Android versions, older iOS, various devices around, and Python. Yeah. So, future. TLS version 1.3 is currently not released. It's in draft form. It's basically fixing the security. It's removing a ton of the broken things, including broken extensions. It limits compatibility. If you're going to be TLS 1.3 compatible, you don't get to be TLS 1.0 compatible. Pick one or die. It removes quite a few of broken extensions, and things like compression support has caused quite a lot of problems, and several other features that are there. It also adds some new elliptic curves, some new forward security things, some features around new crypto in general. So it's going to be fun, big, and huge update, but it's not there yet. So, TLS. TLS is not enough. To have secure crypto, you need some random numbers. This has caused some issues in standards. We have seen the dual EC random number generator attack from the NSA. Basically, they pushed a standard through NIST, who grudgingly accepted it, even though it was known to be slightly iffy. And since NIST standardized it, it means that they could persuade RSA to make it the default random number implementation in their TLS libraries, which only cost them around $10 million US. This is the fact so far. So the RSA takes a known broken, well, not by them officially, random number generator, puts it into the standard, makes it the default, and suddenly the crypto doesn't matter because you can predict the random numbers. Cash, go home. This has hit quite a few others vendors. Last year there were several big VPN vendors that turned out to have problems with the same thing, random numbers. Either badly instantiated random numbers where you could start with 16 states or and just guess all 16. Or you could have had the custom version of dual EC DRBG and could, with the correct elliptic curve to begin with, predict every random number ever generated. Go. Also, we're seeing new bans on cryptography. We're seeing bans in Brazil where WhatsApp and other services are being blocked on the network level because they are unwilling or unable to hand out the private keys of people. We are seeing legal attacks on mail service providers and others to hand over the private keys for things. We are seeing legal attacks on Apple and others to reduce and weaken their cryptography in order to make it easier to decrypt content. We are seeing quite a lot of legal pushes towards vendors, implementers, and others. The good part is that no one is right now proposing new broken cryptography standards yet. However, the TLS is not enough, but it's such a perfect place to start. Quote from Garbage, "The world is not enough," released in 1999. This is how Cloudflare are generating entropy for their certificate authority. Basically, it's a fluff piece, but it gives you proper random numbers unlike other implementations. But it looks very, very pretty. So, next problem is key distribution. it's not enough to have cryptography. You need to get the public keys, you need to validate things, you need to get the data out there. The front page here have quite a few of the old versions. The walk to your bank method is basically where you, the individual, go to whoever you want to authorize, ask them in person for their public key, then you go home and use that public key. It's a very effective way. You guarantee that you trust the person that handed it to you. It doesn't really scale very well. Then you have the leap of faith, also trust on first sight, also known as the SSH model, where you accept the public key of whatever server you're connected to the first time, hope that you're not being man in the middle, and then you get nagged whenever they upgrade or change the domain name, and then you press yes and accept and continue anyway, or whenever they get man in the middle. It solves the problem by not solving the problem. Then we have the web of trust, where you basically manually validate everyone's person and tie them to the key, and then you trust that everyone else are just as good as you are, and nobody ever gets drunk, and nobody ever has a false ID or anything like that, and it turns out that it scales horribly. Very weak to impersonation attacks, and very weak in general. Lots of manual steps. So then we have the relevant models. Trust the government. I mean, they're already handing out ID cards. Why shouldn't they hand out your public keys? Why shouldn't they vet you? Why shouldn't you not trust the government to manage everybody's public keys? Well, we have e-ID cards, where the government in Estonia hand out the public and private keys attached inside the card. Well, turns out that they were broken, and now they had to recall 250,000 ID cards, which was costly, so they just let them continue being broken. Otherwise, governments, well, not everybody wants to trust their government. There's some issues right now in Turkey where reporters really don't want to trust the government, and well, China and all, but we are in Europe. We can trust our governments. Yeah. Pay to trust. That's actually the common version right now. You toss money on someone, you trust that they're greedy enough to keep themselves safe and keep track of things, because greed is a great motivator to do good. Yeah, I'll go deeper into that. Well, you can also assume that the tech is fair, automate everything, trust that the machines do the right thing, hand it over to them, and hope that it works. This one has been integrated into the Pay for Trust version in the form of, for example, Let's Encrypt, which will automatically hand it out without manually looking at anything, and just you hope that the tech is fair. Usually it is. It actually works, sort of. Then you have trust something else. That's a big jumble of things, but it involves things like putting public keys or hashes of them into HTTP headers, so that you say, yes, and our next TLS key is going to be this one, so we can chain them forwards, or it involves putting your keys inside the DNS and hope that the DNS is safe and not intercepted. Well, basically just pushing the problem away to somewhere else. So, before we go deeper into the mess of PKI systems, let's look at what they do. x509 certificates. Take JSON. Everybody knows JSON. It's a nice data format, hierarchical. You can nest them. It has no proper typing and some other issues. So you give it types. Give it a date type. Give it a couple of string types. Let's have, say, 3. 3 sounds like a good number of string types. Let's give it some different integer types as well. 4 or 5, maybe? Various sizes. Let's add some other tags there. And we warp it back into time, and you end up in the 80s. Of course, you need some other things there. You need a way to encode this. So you have the binary format. You have a different binary format for other machines. Byte order, of course. You have a text format, of course. You mean I mean, we need everything in base 64 ASCII because the world is ASCII. And then the 90s came around, so let's add an XML format as well. Yeah. So this is the basic content of a x509 certificate. This is from the output of OpenSSL, so it's decoded, showing you various pieces. Contains a version number, which is a tag, a serial number, which is unique for that certificate, as the algorithm of how it's generated, and then we have some structured data of saying who gave this out, some metadata about when it's valid, before and after this time. Then you have who owns this, and then a public key, some extensions. After that is a hash on it, and then there's a signature of the issuer. So the issuer basically signs the whole blob of data, which means that you can validate that the data inside has not been modified. That's at least the theory. So this gives us a fairly simple way of validating a single certificate. So to do that, you get the certificate from the server down in the bottom. You look up the issuer, and if you don't find the issuer certificate, you fail and go away because you don't trust that guy. Otherwise, you pick up the issuer. Usually, you get the same both certificates from the server, and then you track it down to your own local copy of root certificates, which are on your machine, distributed by someone else, and validate it. And if you can validate the whole chain, check that everything is valid, no times mismatching, no domain name mismatching, no extensions are wrong, then it's okay and you can trust this chain. Puts a lot of trust on the client to do all this validation for every time you connect anywhere. So, in theory, the vendor distributes a CA collection, so the so-called root certificate store, to clients. The vendor in this case is Red Hat, Microsoft, Apple, Samsung, whoever sells the device with the operating system in on it to you. The server then hands out its intermediate, which is who they bought the certificate from, and its own certificate. And then you check the signatures that they match, and then you look it up in your root store, and if that matches, then you have a valid chain, and you can trust that whoever did that is legal somehow. Or at least that whoever signed it did their proper job and made sure that you're connecting to what you're thinking you're connecting to. And there's a couple of different vendors involved. The operating system vendor, Microsoft, Red Hat, etc., ship one copy of them. Your browser usually ships another copy. Mozilla, Google, Opera, all of them ship their own copy of the TLS stack and the root certificate. So in that browser, you're using those certificates and not the system one. And then, of course, you have the OEMs, Dell, Lenovo, HP, who add a couple of root certificates to your store just because they think that you need them. So this brings out the weakness of paid trust. Paid trust. Corporations, most large companies will explicitly man-in-the-middle their employees by setting up blue coat firewalls at the edge point to decrypt and re-encrypt all TLS traffic. That means that they need a signing certificate that's valid for everything, which means that they install a new root certificate on all client machines automatically over the network. So this means that they get paid and they insert that trust, and then they automatically re-sign all the certificates as they go through the firewall, basically acting as a proxy. Then you have the mispaid trust, which is when Lenovo or Dell or Lenovo or HP or Dell again have some pre-bundled badware that they install on all laptops that insert a new root certificate, because you really need to watch all these advertisements, and the only way to insert advertisement in your encrypted traffic is by decrypting it before it reaches the internet. So they install a local proxy to man-in-the-middle you to the internet, because that's the way that they can sell advertisement to others or sell your data to others. This was known as Superfish and the Dell eTrust, and then Lenovo did it again. Then we have the too big to fail one. Too big to fail. Symantec. Symantec handed out, well, we don't really know how many certificates they handed out. They signed Google.com for, Google found at least 200 copies of badly issued Google.com domain certificates signed by Symantec. Several of them signed with 512-bit keys or really weak crypto or ancient hashes that are not supposed to be valid. Sadly, you can't revoke the trust in Symantec because that would break half the internet. So Symantec are really too big to fail. They can keep fucking that up. They ended up handing out over 2,000 certificates, strictly validated and giving you the whole green bar. Everything is dandy to random people. And they don't know who they handed it out to, why it was handed out, or who did it. Türk Trust is the Turkish government. They have been handing out, middleware issuing certificates to various places, including all their outgoing and incoming traffic to the internet. So basically, they have set up man-in-the-middle proxying that automatically reassigns traffic in and out of Turkey to man-in-the-middle all TLS traffic, because you trust Türk Trust. And Türk Trust had to hand that out to the government because the government came with a legal order, said, hi, you must give us this. The rest of the world sort of went on a spree and disabled Türk Trust, but that doesn't really help when you're inside Turkey and you can't reach the internet anymore. You can't really undo the trust in Türk Trust when it's covering the whole traffic. And then we have DigiNotar. DigiNotar is a Dutch company that actually failed. They had their signing certificates on and keys on machines that were publicly accessible on the Office network. They were owned for several months. People, well, they counted at least 3 intruders, and that's why they discovered it, because one of the intruders discovered the other intruder and burned all the walls down. And they've been handing out various signing certificates for both software and domains to people. Well, they didn't do it purposefully, but it was discovered when a big batch of malware hit interesting places signed with official certificates, because DigiNotar had that out. They are actually dead and gone, defunct, no more. So, false trust. Employers, I went into that briefly. Then we have remote administration applications. Many of you who bring your own device to work install this admin thing to track your phone or lock it down. That usually installs a separate root certificate as well in order to be able to monitor and see what all the other applications are doing on the phone. Not all of them are actively intercepting, but some of them are known to do it. Governments, well, I've been talking about Turkey a bit. Kazakhstan took another one. They forced that all computers sold and serviced in the country should have the government's root certificate installed on them. So saying that you legally must install this root certificate, final. And so they don't get distributed by the vendors, so they go around that and enforce it other ways. And then we have various vendors that we trust. For example, TLS has their own signing certificate on one hand of the business, and on the other hand of the business is man in the middle and monitoring equipment to Belarusia and other countries. But of course, they're not handing out signing certificates to those. That would be illegal. So, enough about that. domain validation versus extended validation. Domain validation is the simple one. That's what Let's Encrypt does, that's what Gandhi does, that's what other vendors do. You pay a bit of money maybe, and then you prove that you can either edit the zone file, that is change the DNS to have a special magic record, or put a file on the server. After that, yeah, you control that infrastructure. Go ahead, you own it. It's a fairly simple way. It proves that whoever is getting the certificate is also controlling the environment. It does prove that you're talking to the server that you're talking to, but it doesn't prove anything else. Extended validation. You start with a domain validated certificate, and then you fax the vendor a couple of papers that tell you that, yes, we're really this company. Then you pay them a bit more money to actually look at the faxed paper, and then you send them a copy of your passport, and they send you back the same certificate, but with another extension inside it that gives you a green bar and tells you, yes, we're really this company. They have actually looked at the faxed paper this time. So, verification is difficult. XKCD, of course. You look at it, yeah, this looks like it's signed. Go ahead, we can trust it. The same sadly applies to other software. Most common failures from the client side. Python 276. You connect it to a HTTPS site, you get the certificate back, and it says, yeah, you're encrypted. I got a certificate, that should be enough. It didn't look at the domain name, it didn't look at the common name, it didn't even validate that the certificate was correct. It just accepted, I got a certificate, so it must be okay. Then we do it again. I didn't actually bother to check the signature of the certificate. We actually matched the domain name this time, but still don't match that the public key is signed or that the certificate is actually signed. So anyone can hand out or just hex edit a certificate and give it the correct domain name and it would work. Well, Python again, I didn't really bother to check that the expiry date was correct. So yeah, it expired last year. That's okay. And then we have I didn't bother to check the domain name. Once again, the client has to connect to the service, grab a certificate, look inside it, and this is sadly still the default in Python, because when you hand out a connection or a socket, you actually need to look inside the certificate and check what you connected to make sure that the two matches, because otherwise, well, co-hosting and other things, Cloudflare means that you can connect to the same IP address for many services. It's not always clear if your TLS client is actually doing this. So, more depressing news. Deprecation is now impossible. SHA-1 deprecation was announced for January 1st this year. Everyone was supposed to stop handing out SHA-1 certificates, stop accepting them, and never trust anything that had a SHA-1 certificate. It was signed or had a lifetime that extended past January 1 this year. Miserable failure. Windows XP still does not support anything better than SHA-1, and a lot of vendors really, really like Windows XP. Python 2.6 also only supports that, as well as Android 2.2, and if you're using OpenSSL on the Mac, libSSL, then you don't support anything better than SHA-1 either. So Microsoft has renegated on this one, Mozilla, Chrome as well. Same thing causes MD5 deprecation. It's mostly deprecated now. It's only, let's see, the first attack was 2004, so it's only 12 years that we have known that you can take something signed with MD5, modify a couple of bits, and have it have the same hash. So it's still around, sadly. Most software only gives you a nice little warning that, oh, this is signed with MD5, and then it continues. RC4, also still around, same reason as SHA-1. So, TLS. This is from an Nginx config. This is basically what you need to put into Nginx in order to make it not suck. The defaults are horrible and will accept SSL version 2 or 3, depending on what your libraries support. It will most definitely support TLS 1.0 and 1.1, even though those two didn't even exist when Nginx was built. And the magical SSL ciphers line is, you really need to put that in because otherwise it will use ancient and deprecated crypto. And then we have a couple of headers because it's not enough to do TLS anymore. We need to do it on the HTTP level as well. So yeah, this is sadly state of the art. I can't even fit a proper default inside the slide. You can't read it in the proper one. Stop jumping to. So, in Python, the defaults also suck. SSL context was introduced in Python 3.2 or 3.3. Of course, if defaults are broken badly broken enough to not even be TLS compatible, well, valid, because they are by default accepting SSL version 2 protocols. So this means that Python took the notebook from PHP and created a factory function that says create default context that instantiates an SSL context and returns it with the proper defaults. I'm waiting for TLS 1.3 to be released so we can see real create default context, because we will be broken in when that comes out. Sadly, the state. When I looked at it, the create default context would also create a backwards compatible one, so it will work with code from 1999, because that's the way we do it. Vendors shipping broken tools. OpenSSL has been deprecated on OS X since forever. They have their own SSL API. Sadly, Python does not use that one, so it bundles its own OpenSSL version. This also means that if you've ever used the command line OpenSSL tool in OS X, you have generated broken keys. Congratulations. This leads into the whole factum that all the documentation sucks. So, Python, bundling OpenSSL by necessity, otherwise it would not have an SSL support at all, so they are shipping their own copy of OpenSSL in the build scripts. Of course, Python doesn't release quite as often as other software, especially not on Python 2.7. So the bundled version of OpenSSL in Python 2.7 is outdated, which means that the security issues that came in last week with big news from OpenSSL are still not fixed in Python. So if you're using Python on OS X, you're using broken code. Go. So, picking a cipher. You see the full cipher list in the background here. This is not very useful. In the front run is the highlighted, the one that you really want to use for a current system, but picking ciphers is this. I can't even look at this and figure out what they are doing properly. And I certainly look cross-eyed at them and I wonder which order should they be in, because order is of course important. I don't expect anyone else to do that properly. Old configuration. Python is still exposing in 3.5 as well as 3.6 Git the SSL v2, v3 that has been deprecated for ages and are not supposed to be used. So instead of exposing the protocol TLS version, we are exposing the don't. So you say, I want to use TLS, I want to use SSL v2 and 3, and I don't want to use SSL 2, and I don't want to use SSL 3. Yeah. The documentation around this is not very helpful, and the Python code is going to be painful for you if you're doing it wrong. Documentation never dies. There's still a function called SSL.WrapSocket, which causes issues because it's doing SSL2 versions. So we add another function to help it. Upgrading is hard. Getting up into new TLS 1.2 is difficult. And Python 2.7 may never upgrade past TLS 1.2. So whenever you think about supporting TLS 1.0, imagine running your code in Python 1.6. That's the question you should ask. Why? There's a couple of fixes, but I think I'm running out of time. So sadly, I only get to show you this one. This is how you do it today. And this is how you do it in CherryPy to actually set up proper defaults. You can do it in Python. It works. The highlighted lines are the lines you need to change in order to go from HTTP to HTTPS with proper encryption. Yep.
Maybe we can stretch like 5 minutes for some questions.
Just a quick question. What version of Python was the last example you showed? That example.
That example looks like Python 2 and 3.
Okay.
That's just a system package of CherryPy installed on a fresh Ubuntu 16.04 machine. It's CherryPy 3. This is their Hello World example with SSL support added. And this is the command line you run to get your certificates.
There is one more.
Yeah, so thanks for the great talk. Question about Python as a client.
Yes?
Does it do any revocation checks currently?
No.
Okay. Yeah.
Revocation checks are outdated and should not be used anyway because you're leaking what you're talking to in clear text. It adds a clear text channel. So
yeah, stapling fixes some of that, but yeah.
Any more questions?
Over there, in the middle. Anyone else while we're waiting for that mic?
Any other questions?
How susceptible is TLS to fingerprinting? Like finding out what machine you are running, what kind of applications you run?
So, that's a good question, and quite so. You're doing the handshake when you're deciding which ciphers you support in clear text. When you first connect, you're doing the clear text handout of cipher list and such before you establish a connection. And that list is unique between versions. So the domain you're talking to and your specific configuration is leaking. Various SSL libraries support various ciphers, so you can fingerprint them. You have a harder time to fingerprint other behavior, but after that you have timing behaviors on the traffic inside. For example, how you set cookies, how you set everything else, which can allow you to fingerprint down on a better way to figure it out. So it does not protect your metadata.
That's all, and thanks for your fantastic task. Yeah. So give a big hands. Now lunchtime, you can go straight ahead and you'll find your place. Yeah.